Well, hello, thanks for watching this video. I assume if you're watching it, you want to learn a little something about how you calculate a center of mass. So I'm going to show you a couple examples, and just so you know going into this, this is not going to be one where we have what we call a continuous mass distribution, a fancy name for kind of an extended object. That would require calculus, and we're just not going to do that in these examples here. So we're going to find more what we call just a couple of different particles kind of arranged together, and we want to find what we call the center of mass of those. You may have heard this called center of gravity before. There is a slight distinction, but as long as we're near the center of the Earth, or the surface of the Earth rather, we don't really need to worry about the difference between center of mass and center of gravity. You can also think of this like the balance point. So if you had a collection of objects and you were trying to balance them at one on like a fingertip or something, you would have to balance them right at the center of mass, sometimes called the center of balance. So let's look at an example of one, and I'm going to draw myself a little coordinate system here, because anytime you calculate a center of mass, what you're really looking for is a location, a point in space, or we're going to describe it as a coordinate, just like an XY coordinate. In more advanced problems, you could have an X, Y, and a Z. So in my example here, I'm going to use a 2 kilogram object here that I'm going to put right at the origin. I'm going to put the number 2 to represent 2 kilograms. And then over here, I'm going to have a 4 kilogram object. Let's say that's at 3 meters along the Y direction. And then let's say 3 meters over here on the X direction, we'll have a 1 kilogram object. And then another 3 meters over, we'll have another 1 kilogram. So these are each 3 meters. And so somebody says, for that arrangement of 4 objects, what is the location of the center of mass? Well, the equation for the center of mass, it's really an equation for each of the coordinates. The x coordinate of the center of mass, we denote it that way, can be found by taking the inverse of the total mass of your system and then a sum. A sum is just adding up the total contribution of each of the different parts. So we use this little counting scheme here. So I is our counting number. We count up to the number of parts that we have. That's called n. And then what are we counting? We're going to count the product of each individual mass times each individual's x coordinate. And these really are vector coordinates, because sometimes you'll have things to the left of your origin, and we'll have to count those as negative. We do a similar thing for the y coordinate of the center of mass. 1 over the total times the sum of all of the contributions of each of the parts, n number of parts. So a lot of symbols here, and I know that can look confusing. I'm going to show you in this case what that calculation looks like. So my x coordinate of the center of mass would be 1 over the total mass, which is 4, 2, 1, and 1. That's a total of 8. And then we'll just say kilograms, but I'm going to leave the units out just for clarity. And then I'm going to add together all of my parts. So I've got 4 things to add together. And each of those things is a product of a mass and a coordinate for where that mass is located. So I can just start at the top one here. So I would use 4 kilograms times its x coordinate, which is 0. And then I'll go to this piece here. It's 2 kilograms times its x coordinate, also 0. And then this one is 1 kilogram times its x coordinate of 3. And this last kilogram here, 1 kilogram located at 6 meters away. So it has a coordinate of 6. So then we just have to do all the math. Now obviously these first 2 terms don't count for anything. This total in here is 9. So the x coordinate is 9/8, or 1.125 if you like it in decimal form. Now where is that? Well, here's 3 over here, so we're just about here along the x-axis. So I know it's somewhere along there. And then we do something similar for the y. And I'm not going to write out the formula here, but just like we did before, 1 over the total mass of 8. Now I'm going to add up each of the contributions of the parts, but I'm going to use their y coordinate. So Notice these three pieces here, their y-coordinate is 0. So just to keep things simple, I'm not going to write those because they're just going to add up to 0 anyway. So I have a 0 and a 0 and a 0. And the only one that has any y-coordinate that's not 0 is the big guy up here, 4. So it is the mass of 4 times its y-coordinate of positive 3. And so that adds up to 12 over 8. Or, putting it in a form that I prefer, decimal form, that is 1 1/2. 1.5 meters. So where would that be? That's halfway up here. Does that make sense? Notice we have 4 here, and we have a total of 4 down here. So the center of mass is exactly halfway in between them. So here is that special point we call the center of mass at this coordinate of 1.125 over and 1.5 up. So what other form could this take? Well, imagine we have a disk with a radius of, let's say, 5 meters, and the disk will be 4 kilograms. And imagine we have attached to the disk, maybe halfway over, another little hunk of mass. I'm going to darken it so it looks like something stuck to it. Maybe that's a 1 kilogram mass, and it's located 2.5 meters away. So that's just half the radius. Where would the center of mass be for this? Well, we can tell just where it's located now that the center of mass is going to be somewhere along this line, if you would imagine balancing it. So I just need to find really the x-coordinate for that. So the x-coordinate of my center of mass. Now what I'm going to do is I'm going to take the big 4 kilogram disk and I'm going to treat it as though it's just a single 4 kilogram dot of mass right here at the center. And this is something that's nice about the center of mass calculations. You can always it's almost like an abbreviation or a simplification of your extended mass just to use the center of mass of the disk, because if I ignore the little extra mass sitting here, the disk of course has its center of mass right at its geometric center. So I'm going to pretend I have 4 kilograms there and 1 kilogram here, and so I would say 1 over my total mass, which was 5 kilograms. And then each of my parts, I only have 2 parts, I have 4 kilograms, basically at my origin. I'm going to use my origin right there as though it goes through the center of the disk, so its x-coordinate is 0. And then I have the other 1 kilogram mass at an x-coordinate of 2.5. And so where is that? Well, this adds up to 2.5, put that over 5, that ends up being 0.5 meters for the x-coordinate of my center of mass, which is kind of hard to see here, just a little bit to the right of where the center of the disk is. So all that did by putting that extra mass there, shifted the center of mass just a little bit over, actually it's 1/10 of a radius over from where it normally would be if we didn't have that mass sitting there. So those are the most typical examples of center of mass calculations that you have to do. If you need anything more obscure than that, you could ask for help from somebody or look that up in a reference of your choice. Hope this was helpful. Thanks for watching.